All right, I think we can finish this up. We only have 8 slides to go, and some of them are probably placeholder slides. So here's our flying pig. We have a pig. It hangs from a string, and if we give it turn its little wings on and give it a push, it'll start flying around the room in circles. You can probably find a video. I know that I've already posted videos of this myself on Facebook and on YouTube, so you can go see a flying pig if you want to. How many forces are acting on the pig? So I see a force of gravity on the pig and pulling the pig down. I see a string on the pig, pulling the pig up at an angle, right? A tension in the rope. So there's a tension in the rope, and there's a force of gravity. And I think that's it. Is there acceleration in the vertical y direction? No, the pig is not moving up and down in the y direction. Is there acceleration in the x direction? Yes, it's a centripetal force inward on the pig because it's going in circles. Question 3, the free body diagram of the pig would be, here's the pig, here's the force of gravity, here is the tension in the rope. We don't draw centripetal forces on free body diagrams because centripetal forces are caused by other forces. In this case, the centripetal force is caused by the x component of the tension. And using not safe for work, what? Use NSL for the x direction and the free book to solve for velocity in terms of GR and theta. Don't forget the equation for T from question 5 and the equation for centrifugal acceleration. Solve for velocity in terms of GR and theta. What? All right, so the y component of the tension is equal to mg, and the x component of the tension is equal to centripetal force, which is mv squared over r, and the so basically v squared equals gr, or v equals the square root of gr. I don't know where the theta comes in. We can't use the equations that have a big G and a big N in them because those are only for things orbiting planets. It's Newton's universal law of gravitation. The tension in the string will be greater than, less than, or equal to the weight of the flying pig. I'm going to say the tension in the string is greater than. A component of it is equal to the weight. So the full hypotenuse tension in the string, the hypotenuse is always greater than a leg. So the y leg of the tension will be equal to the weight. So the hypotenuse is greater than that. Using Newton's second law, oh, that's NSL, Newton's second law, in your free body diagram for the y direction, solve for tension T in terms of mg and theta. All right, so tension, oh, that's where the theta comes in. So T sine theta equals mg. So tension is equal to mg divided by the sine of theta. Yeah, it's the y component, which is equal to mg. So for the one we did up here, oh God, what are you doing, dude? Okay, so T cosine of theta is equal to mv squared over r, and yeah, so this is not right because that was T sine theta, which is equal to mg over. So we could put in for T, we could put mg divided by sine theta times cosine theta equals mv squared over r. So the m's cancel, that's still true, and the gr's, so v squared is equal to gr, but it's a component, it's the cosine over the sine, which I think is, it's like sine over cosine I know is tangent. I'm not sure what cosine over sine is. I'm not even sure I did it right. I'd love it if you straighten me out. It'd be gives a good time to talk. What's the relationship between the acceleration of the pig, v, and the radius of the circle? Why is this acceleration called? It's centripetal. So the centripetal acceleration is equal to v squared over r. It's inward. Wow. Well, that was a... And that's the same thing twice, probably because one slide was for me to talk over and one slide was for you to draw on. Two orbits of two planets of equal mass that orbit their star in the counterclockwise direction as a double planet system. From the point of view of an observer on either planet, the planets appear to orbit each other while also orbiting the star. The dots on the orbits represent the position of the planets at time t0. And x is the position of their center of mass at that time. Which of the following arrows best represents the acceleration of the center of mass of the double planet system when it's at point x? Inward, because it's got centripetal force from the planet. So I'm going to go with that. Pointing at the star. A uniform plank is placed with a pivot at its center. Yeah, it's called a fulcrum. The block is placed on the plank to the left. The student is asked to place a second block of greater mass on the plank so it will balance when horizontal. Which of the following quantities are needed to determine where the second block should be placed? Select two answers. Since it's at the middle, I don't think the mass of the plank matters because it's center, right? So the torque of the board is going to provide torque on both sides, but that's going to cancel. It would be nice to know the mass of the block, right? The blocks would be good to know. And the distance from the pivot to the left block. And if we knew those two things, then we could find the distance over here on the right side. So I think B and D is where we're going to go. And there's the same slide. Well, this goes really fast when you have duplicate slides. The system consists of two spheres of mass m and 2m connected by a rod of negligible mass. It's held at its center mass with a rod released to the surface of the Earth. The graph shows the rate of change of linear momentum of the sphere of mass m. What's the linear momentum of the two-sphere system at time t3? So this is showing the change of the linear momentum. It's going to change by 15 units, right? Released from rest. And so what is the linear momentum of the two-sphere system? It changes by 5 units of momentum every second. I think it's 15. I don't know why they got to, yeah, I think that's it. I think that question tricked me in the past, so I'm a little nervous about that answer, but it seems kind of straightforward to me. So I'm probably having some blind spot. What's the mass m? What's the n here for? What is that? Is that newtons? Is that supposed to be in newtons times time? That would give us momentum, so. Oh, why the system does not rotate around its center of mass as it falls. The Earth exerts the same gravitational force on both spheres, causing them to accelerate at the same rate. So C and D look like good answers to cross out. It doesn't exert the same gravitational force on both spheres. They have different gravitational forces, so actually A and B are good ones to cross out. Right, same gravitational force on both spheres? No. Gravitational force is mg. They have different m's. They have different forces of gravity. Larger gravitational force on 2m. Okay, these are both, that part's both true. The sphere closer to the center of mass and the torques cancel out. What? Well, that's true. It has more inertia and the torques cancel out. I just think that more inertia and the torques cancel out. I don't think that has anything. I think it's C is Probably the best answer. I don't know. Again, it would be better for Burkhart to look them up ahead of time. I usually can explain the answers a lot better when I know what they are ahead of time. That's the end of the show, though. So please reach out to me if I did anything wrong. I'd like to talk. I'd like to share my. I would like to be humiliated in class, and you could tell me why I was wrong on 29 or any of the other ones. And have a good day.